things. So we can probably get started with the first speaker, Vinicius.
Yes. So thank you, Dr. O. I think it's a great honor to introduce Vinicius. I just look at LinkedIn. Vinicius is actually medical doctor in family medicine, and also he's outstanding AI PhD candidate in Brazil, University of São Paulo. So I think we're going to have a great time from his speech. Thank you. Obrigado.
Thank you so much, Young. Hi, everyone. I'm Vinicius Almeida. Thanks for the invitation, for being here. I'll just take a minute to share my screen.
Nice, visible.
Okay.
Yes.
Okay. So, as Young said, I'm a family doctor from University of São Paulo, and I'll be talking today about a recent paper we've published, which is called Large Language Models as Medical Code Selectors, and a benchmark using the International Classification of Primary Care. And of course, I'm here representing several colleagues who also contributed to this work. So first of all, why talking about medical coding? Medical coding is a tool that helps us make sense of healthcare data. There is a lot of complexity in healthcare data that is present in the electronic health records and other healthcare softwares as well. And that includes a lot of unstructured data, especially in the form of text. And medical coding helps us organize that information to create meaningful insights about population health, research, and even insights about the work of healthcare professionals. And ICPC, which is the International Classification of Primary Care, is currently the most suitable classification for this setting in the healthcare systems. And that's the case for a bunch of reasons. So one of those reasons is the high agreement rate that we can achieve among coders. So in this specific study, experts in ICPC coding demonstrating to reach a very high agreement rate level. And even for people without training, or with just a little bit of training, the agreement rates can be quite good. And on the other hand, when we look at different classifications, such as the International Classification of Diseases, ICD-10, when doctors code the same patient records, they achieve pretty bad agreement rates, especially when we talk about more specific codes, which are those with 3-digit or 4-digit codes. And the impact of changes in coding practices can be huge. So in this graph, you can see the incidence of sepsis in United Kingdom hospitals, which increased almost threefold, only because between 2017 and 2018, there was a change in the way this diagnosis of sepsis was coded. So here we didn't have any change in disease behavior or even in clinical protocols. And we also know from a previous study of ours that semantic search using large language models embeddings is a very good and promising way of retrieving codes, relevant codes in a search engine. So this achieves a much better result when compared to traditional ranking algorithms such as BM25 or even Levenstein distance. So the main objectives are first to evaluate the large language model's capacity to automatically select adequate ICP-C2 codes from a list of results from a search engine. We wanted to estimate the impact on performance of the size of the results list, and also estimate the impact of improving the retriever. So what happens if we improve the search engine itself? And also understand the relationship between performance, cost, token usage, model size, quality of answer generation, and so on. So in order to do this, we created an evaluation data set with clinical concepts, which come from real-world queries from healthcare providers in a search engine for medical coding. And these clinical concepts were annotated by peers with experience in ICP-C2. And in this heat map, you can see that although not every code in the ICP-C2 classification was represented, we were able to cover all chapters of the ICP-C2 classification. And in the next slide, we have also the process codes, which are also part of the ICP-C2. We evaluated several large language models and included both open and closed source models. And this is the prompt template for you to know how we interacted with the language models. So the models received a query, which was a clinical concept, and a list of results from an ICP-C2 search engine, which was powered by semantic search. And we found that models could achieve a pretty good performance in terms of selecting an adequate code from the list of results, and with the top models being leading models from OpenAI, Google, and DeepSeek. And it's worth to notice the presence of open source models as well in the top of the list, such as DeepSeek, Llama, yeah, mainly those two. And this graph is to show how performance relates to cost. So it's important to notice that the x-axis is the price, and it's in log scale, and the performance is in the y-axis. So ideally, in this graph, we want models to be cheap and powerful, which is in the top left corner. So one insight that we can take from this is that if we compare the leftmost model, GPT 4.1 Nano, and the best performing model, GPT 4.5 Preview, there is a 10% difference in performance, while there is 1,000 or 10,000 times difference in price. So that can help you decide on what models to use, depending on the resources you have and the performance that you need in your application. And this is the relation between model size measured in billions of parameters and performance. And we can see that performance increases noticeably with model size, but that correlation is much weaker after 30 billion parameters models. So what differentiates models above 30 billion parameters is something different than model size, probably related to how they are trained, what kind of data they have in their training phase. Another interesting aspect that we've seen is that the relationship between performance and token usage is not so strong. So well, we can easily see that there is no meaningful correlation between token usage and performance, which means that reasoning alone is not sufficient or efficient enough to improve performance in this task. And here we can also see that most models were able to generate an answer that corresponded to the request format. Only very small models failed in achieving that, such as the 1 billion parameter Llama model or the 1.5 billion parameter DeepSeek Qwen model. Most of them achieved 100% of correct answer formatting. Now, considering only the answers that had the requested format, most models also returned a valid ICPC2 code as an answer. Since code hallucination is one of the concerns, using LLMs in this structure removed almost entirely the hallucination of codes in the LLMs we tested. And finally, not only we want an answer in the valid format and with a valid ICPC2 code, we also want the models to select codes from the list of results. And we can see that in almost every answer, most of the models were able to select a code from the list of results they had access to. This way, the differentiation between those top performing models happened in their ability to select adequate codes from the results list. And inspecting the output of reasoning models, such as DeepSeek R1, we also had a lot of insights since it reviewed some imprecisions in the evaluation dataset. And this was particularly evident in situations where multiple codes with similar meanings were retrieved when we had an ambiguous query. So instead of treating these terms as simple synonyms, the DeepSeek model applied reasoning to analyze the nuances between the candidates. And we have this pretty interesting example here in which the query was drug use, and the model was presented with codes related to both recreational drug usage and substance abuse disorder. And although only one was considered relevant in our evaluation dataset, the model's reasoning processes led it to consider both options and reviewed a mistake in the data annotation process. And this behavior reviews a potential application of reasoning models in large-scale data annotation for spotting inconsistencies in human annotation. So the vision behind this work is that with automated medical coding, we could achieve near real-time population health monitoring. So we could have insights on quality of delivery of healthcare that could help us with data-driven decisions about population interventions, patient outcomes monitoring, research, and so on. So we have a huge field of applications. Well, and this study is available as a preprint in arXiv and was also accepted for poster presentation in NeurIPS this year in the Gen AI for Health workshop. So if anyone is interested or willing to talk more about this, please get in touch. I think we can go to the question answer right now.
Thank you so much for the presentation. If anyone has any question, please go ahead. I also have some questions. So I wonder, so you also mentioned that in one of the experiments, the model size was not kind of plateauing, right, as you increase the model capacity. And you conjecture that this may be due to kind of the lack of right data in those models anyway. So increasing the model size and the data size is not exactly kind of helping with this particular task. I have not been following the state of the art in medical AI foundation models. Have you looked into these models as well? And do you think there's some use in these models?
Yeah, our benchmark tried to investigate the leading large language models in the industry at the moment. So we didn't evaluate specialized medical LLMs. Um, so our results could be different if we had more specialized large language models. So I think the reasoning behind an adequate code selection in this very specific task is also a very specific kind of reasoning. So I think we would need a more um, uh, directed, a data set more directed to this task specifically to make it more efficient. So we already have some experiments ran using reinforcement learning in this context, and very small models are able to become much better in selecting good good codes only with a small data set. So this is very interesting because we possibly don't need very large models to accomplish this, and possibly we don't need much data
Mm.
as well.
But by fine-tuning, what you meant is like still starting from some generally trained, pre-trained model, right?
Yeah,
Do you
yeah.
think? Yeah. Mhm.
Just to mention, this experiment that we did and we are willing to publish in the
Mhm.
future in a future time involved the worst model actually in this study, which was the llama with 1 billion parameters. So we took that model, we created an annotated training data set. So, and we used reinforcement learning because this task of medical coding can be framed as a very as a reinforcement learning task with verifiable rewards, just as math or coding. So
Mm.
when we give the right reward, these models learn to better select the codes uh, among the results of a search engine.
Mhm. Maybe a very ignorant question, but I wonder if RL is really needed, or maybe just a simple classification is already doing a job. Mm.
Yeah, I think that the problem with the classification is that in general, for medical coding tasks, you have a very large label space. Uh, so we are talking about hundreds or thousands of
Mm.
different possible classes. And
Mhm.
that's why associating a search engine to the context, you can reduce a lot the number of options
Mm.
available
Mhm.
for the model, and you
Mhm. Mhm.
make it a very much easier task
Mhm.
for a model to to do it.
Mm. So you want to keep it more generative instead of just fixing the, how to say, like the candidate set. Mhm.
Yeah, that was our hypothesis when doing this. So we imagined we could use
Mm.
less data uh, and achieve good results just by adding the search engine to the model context.
Mhm. Mhm. Um, I have a few more questions, but if anyone else has any questions, please go ahead. You can always stop me and just um, otherwise, since you are also a medical doctor, like a family doctor, you said,
Yeah.
or yeah, or Jongmin introduced, I think. So I
Mm.
wonder if I mean, I'm also coming from the more technical, I mean, how to say, like more engineering background rather than more practice. So I wonder if you find these techniques really useful in practice, or do you still think there's some gap to close?
Yeah, I think, for example, for the ISPC2 coding task, we still have some gaps in the pipeline. So to make a working system from end to end.
Mhm,
So we can already use, for example, LLMs to extract meaningful concepts from health records. But we do not have, for example, a good benchmark or uh, data showing how good these models do that. So I think we still have that missing part. But as soon as we have the extraction phase done well, the code selection phase done well, even the code retrieval done well, we have the entire pipeline. So then all we need is to make that efficient enough to apply to electronic health records and scale that. Um,
mm.
so that's basically the vision here.
So to understand the problem better, so would you agree that scalability is the main kind of one of the main bottlenecks that you wish to tackle?
Yeah, that's one of the things.
Hmm.
And I believe we can achieve that by training these small models
Hmm.
for code selection and extraction of the concepts.
Hmm.
And given the results of the study, I really think we can achieve that. And of course, that would enable as well to respect data privacy while integrating to electronic health record systems. So that would enable, I think, scaling this kind of solution.
Hmm. Okay, yeah, I think these are very important points that you probably don't want to send data anywhere, so you want the models to be lightweight. Um, and by so by bottleneck, I guess still my question is whether this kind of classification task, although yeah, this is not technically classification, but like making this classification of the codes. Um, do you think that's kind of an important bottleneck for kind of the everyday work pipeline for doctors as well? Or I guess I'm wondering if the time it takes, I don't have good idea of how much time it takes for the doctors to actually complete this task. Maybe they have to kind of go through the manual and kind of read the definitions again to kind of make the right choice. Or maybe I was imagining we can help them reduce the error. Maybe I thought that could be another contribution.
Yeah, yeah, you're absolutely right. So first thing, medical coding is not a priority for healthcare professionals in general, at least when they are not, s- well, at least when they do not have financial incentives to do that. So in many countries, doctors' payment is based on they completing the coding part of the consultations. I think that happens in the US and in many countries in Europe. In Brazil, that's not the case.
Oh,
So doctors in general do not worry much about the code they select. So at the end, we have data, but with very bad quality. So you can't really trust the code the professional selected. Um, so that makes a huge problem because you kind of collect tons of data every day and you can't trust that code. So
mm,
if you have an automated system to do that for you, you can remove that time from the healthcare professional and also increase the quality of the data you're gathering. And with better data, you can, for example, predict the population demand in terms of clinical complaints, chronic diseases. You can use that for research. You can plan for like population interventions in your healthcare institution. I think every data science study using a better data can benefit from that.
Yeah, okay, that's really informative for me. That's such a nice motivation.
Thanks.
So if anyone else has any question, otherwise we can also move on.
Okay. Let me remove. Okay, so now let me introduce Dr. John Ming Kim. Dr. John is a professor of statistics at the University of Minnesota Morris, and also adjunct professor of finance in the EGADE Business School in Tecnológico de Monterrey. Welcome, Dr. John.
Thank you. Muchas gracias. Obrigado, Vinicia. Okay, let's share screen. Okay, the first screen. See, first screen. Oops. Oh, first screen. Okay, so this work is a joint work with Jung-Jin Lee. He's a PhD candidate in Division of Biostatistics, Ohio State University. So I interested in the drug treatment. Then I just introduce what's a drug discovery. This is a kind of a drug study, the high cost and long development timelines and high failure rate. So many small company actually bankrupt. Actually, they spend 10 years, 15 years, no money, then they bankrupt, delisted from U.S. stock market actually. So it's a high risk actually, and declining R&D efficiency too. So I think AI nowadays accelerated discovery and automated complex analysis, and then identify novel drug target and enables data-driven decision making. Actually, my side is more data-driven decision making. So kind of now target identification. Now we have many multi-omics data. So we can integrate it to pinpoint disease associated genes and proteins and models and biological networks to reveal critical pathways. Also, this is interesting what already some NASDAQ company, bio company, they use AlphaFold predict protein structure to assess drugability. I think that's promising area very much. So many other countries they are focused on develop the drug now by using this kind of program. And also economic impact. So you can save money. Actually, that's very important. Also, you can save time to market and improve clinical success rate and boost biotech valuation. The issue is FDA approval. Still, they are wondering this drug is good for patient. That's the question mark actually. So also technical limitations, data quality, and bias, lack of interpretability. Because this is kind of a deep learning method they're using inside. The high computational demands, now many company, big tech company now, they are building data center, but still we need the power to run this data center. So still kind of there are limitation for now. Also, this main issue is data privacy issue. This is confidentiality. So, and algorithmic fairness and accountability in AI-driven decision. For example, like Tesla, uh, uh, car. Now that they have no driver and automatic driving system, issues that they have a car accident many times nowadays. Who is responsible? That's the insurance issue too. So I think the insurance company more interested in this side too, actually. So AI is enhance human capability. It does not replace scientific expertise. And still we need a human insight, like a medical doctor, physician. Researchers remain essential for interpretation, experiment design, and critical judgment. So drug discovery will increasingly rely on synergy between data scientists like me and biologists and chemist or medical doctor. So AI is a very promising area because this we can handle large data set to predict individual treatment response, like a precision medicine, okay, and maximize treatment efficiency while minimize adverse effect. So I think pharmacogenomics is promising area. Also, my side, we do predictive analytics. We use machine learning technique, identify real-world patterns to determine which patient benefit most. That's my job, actually. And then applications guides physicians in selecting optimal drugs and dosages, particularly for complex diseases like cancer. So that's my research area, actually. So this is recent my publications. So far, I'm doing more now. Jongjin and I, we just published the linear case. I'm going to introduce the first three papers quickly. Linear case and then non-linear case boosting method. That's the second revision, Journal of Royal Statistical Society, CDC, and already published Series A. Now, third paper is a first revision from lifetime data analysis. That's SSCI journal, good journal in survivor, specialized survivor. And another paper is a COPLA method. COPLA mean is couple. So this more we consider dependence structure inside the mother. So this is we submitted to Biostatistics journal. That's also a good survivor medical journal. So why Q-learning for survivor? That's my idea 2 years ago. When I visited the Seoul National University Department of Statistics, people there are talking about reinforcement learning. So reinforcement learning, simple idea is about we do reiteration, then you make a decision, like online game. You go left or you right to win, game. So you need to make a decision by using reinforcement learning. So then I realized that maybe it's a good idea we do more survival analysis to apply. But survival data, you have a doctor here too. There's sensor data. What means sensors? Because we have some experiment. We have a certain time, maybe 1 year. We have a limited budget, 1 year or 2 year study. But event does not happen until 1 year or 2 years given time. Then we just drop out. That's the kind of in survey sampling is missing data. So in survey sampling, if you have a missing data, some people just throw away. But then you have some
kind of issue or bias or overestimation issue actually. So in survey sampling, they consider how to impute to this missing data. That's the main research in survey sampling nowadays. Yeah. So in same idea too, in medical study, many missing data. So many people, this is money actually. Individual data is very expensive. You just throw away money, then you don't have much data actually. So how to impute data? That's the question in this research. Okay. So when outcomes are censored, then direct Q-learning cannot compute the full reals biasing learned policies. Okay, so I think that's the every time you need to make a decision, life is a decision, sequential decision. That's very promising research area. I just submit to JASA too. Sequential decision making very important. That's why, you can maybe good decision, maybe high reward. In medical study, good decision, good optimal dose, that makes someone live longer. Okay, that's our goal in this study. Okay, so example, switch therapy if viral load increases, or otherwise maintain current dose. That's the kind of doctor decision make based on this decision actually. So we maximize expected total survival. That means reward. Okay. So Q function concept is I told you like it's the online game. You go left, we go stay, or you go right. Okay. So you just do reiteration. Then we do expect to remain survivor given current action and history. So recursive structure backward induction for optimal policy. Okay. So at each stage, BJQ, Berkeley James Q learning, we named, learns the expected survival reward and chooses the action, maximizing future benefit. That's our goal. Okay. So why sensory problematic? You know that I already mentioned. If you have missing data, censoring means missing data in survey sampling. Okay. Then you just throw away, then not many data remaining. That's also expensive. So our goal is we use Berkeley James method to impute the sensor times consistently, and then we apply Q-learning. Okay, that's the small idea, but very important. This idea can apply to many different subjects in medical study too. Also AI study too. Okay. So who made this kind of idea? Accelerate the failure time model. Actually, log t, okay, then a linear equation for log time, okay? So more interpretable than hazard ratio in Cox model, okay? So Berkeley-James estimate impute sensor log t. It kind of interesting method, but it was not that popular until 2000. Then more we have a nice computer. Then people had a good computing facility. Then they start to making this model feasible. Okay, so 2000. I think 4 5 Jin Chen in Columbia University, the biostatistics. He's a Korean Chinese. He made a nice publication. This method, okay, estimated how to do estimation. Okay, he did a wonderful job. Then more and more people they're working actually. So we use more Jin Chen method. Korean name Kim Chol Jin. So replace the census outcome with each conditional expectation and then compute using Kaplan-Meier estimate for residual distribution. Okay, this is a Jin Chen method actually. Then the iterative Berkeley-James estimation and they show converges rapidly in practice, retains the asymptotic normality of the least square estimator. Okay. So, also we can apply to double censoring extension. Double censoring mean is what? Uh, interval censoring, left to right to interval censoring. So 2 years ago, someone, didn't have cancer, but 2 years after, then the person went to see a doctor, then doctor said, you have cancer. So we don't know what happened actually. 2 years ago, the person was fine, patient was fine, but after 2 years, he got cancer. So I don't know when this cancer started. Okay, that's kind of interval censoring idea. So we can apply left, right, or interval censoring. Left mean event already happened before the study started. Okay. So this is the idea is very simple. We just integrate BJ method Q learning. Okay. Then we do optimize survivor. Okay. So we just use a decision. Okay. What's the predicted survival under the each treatment option? Okay. You stay, dose, or decrease, or increase. Okay. So we select the one yielding higher expected value on the regularity conditions, consistency, positivity, exchangeability. So this is simulation study, 50% censoring, 50% maybe missing covariate. Covariate mean kind of the patient information, okay, introduced, okay. So and then censoring time is drawn from 20th, 80th percentile of a total survivor. This is a kind of similar setup. It works well. So this from this box plot, we see the true, this single stage, I just do single stage, no second stage, okay? Not sequential. This single stage case, they show BJ linear Q, it looks better than Cox Q learning, actually. We need to compare. Cox model is most popular citation paper in biostatistics survival analysis. So they recommend, hey, compare Cox model too. So we compared, but the BJQ method is much better performance, okay, close to real value. Okay, second, that's the result of summary statistics accuracy. You can see the increased sample size from 100 to 1000. The accuracy is very good. Okay, BJQ. So and then two stage same situation too. PJQ is better than CoxQ. Okay, so then we just use our package data HIV patient data. Okay, then compare this DDL monotherapy and the AGT plus DDL combination. Okay, so then 75% to right censoring, that's pretty high in, missing CD4 and baseline covariate. Okay, so we are outcome days until CD4 drop more than equal to 50. That means age, AIDS, age, and or death. So this paper is a contribution is a kind of a, we can integrate reinforcement learning with the survival analysis, and we can handle double censoring and missingness. And then, this is outperformed compared to Cox model. Okay. Then next project, this is the topic boosting method. Okay, I did a pretty successful linear case, linear model, log linear. Okay. Then we look at the boosting method of Berkeley James, 2010, JASA, Journal of American Statistical Society, main top journal, published Berkeley James boosting method. Okay, let's apply nonlinear case. So I don't know much about medical data, but sometimes it happens that the data type may be nonlinear type. Okay, not often, but some cases it happens, I guess. So let's apply Berkeley James boosting method to this paper. Same idea. We just iterative boosting, okay? Component-wise least square or tree, okay? Method. So advantage is directly models conditional survival time for robust imputation avoiding restrictive proportion hazard assumption. Okay, that's the highlight part. Okay, so that's same thing, dynamic treatment regime, sequential. Okay, history, you make a decision, then you look at the next time you visit, then you just doctor job is what? Hey, we need increase dose. That's disappointing. Or we need increase decrease dose. This is a doctor look at the data, then make a decision too. So here is visit 1, visit 2, visit 3, and failure. So some patient come first time, second time, maybe we stop here, then kind of the censoring, right censoring case too. Some people happens, but otherwise failure. So this is a censored case. Then next step is the same idea, but existing method is a limitation. Cox-based queue learning rely on proportion hazard assumption, which can reduce bias on the non-proportion hazard. Okay, so then we would suggest, hey, maybe we tried nonlinear case. So we semi-parametric handles the censoring by iteratively imputing sensor residuals. Okay, linear case may incur moderate mystification. That's the kind of a point. I don't know much medical data. Maybe finance data it happens a lot, but medical data, most human being data, so not much high fluctuation, but it can be some cases. So this is a linear case I already mentioned. Now boosting method looks like flexible, okay, and capture interaction nonlinear effect. So direct modeling of log survival with flexible based learners, okay. So this procedure, same thing. Uh, we make it earlier this stage, and then next stage we estimation and make a decision. We need to increase dose level or not, or stay. Okay. So concept is interactively we do. So everything is wonderful. The twin boost tree boosting algorithm. Then we can recursively update to imputed outcomes and Q function to improve policy estimation under censoring. Okay. So this is a kind of same procedure like linear. Okay. So just to show output, maybe trade-off, flexibility versus overfitting. So we control your boosting iteration by and the shrinkage. Okay, and then similar setup. You can see here 50% right censoring. Okay, this similar n equals 500 patient, 1,000 patient. Okay, and then the BJ tree method looks like a kind of a this IQR is small and more accuracy to real data. So it works well. Then coverage of optimal treatment in the stage 1, stage 2, pretty high compared to other methods. Okay, so multi-stage clinical trial, same data we apply, then here is the output. The single stage analysis using real outcomes looks BJLS in onset time only BJ3 looks like compared these two methods, tree method is better than least square case. Okay, and then also the recommend treatment is slightly different than LS and tree. Okay, method. Also, here is a two-stage case, which looks like much better. Um, one mean increase actually. So there's combination case. Then tree method looks nice too. Okay, so main contribution here. We applied the Berkeley James Boost Q learning framework for sensor survival data. Okay, and unified AFT-based imputation with recursive Q learning enable to flexible interpretable dynamic treatment regimes and demonstrated robustness to non-proportional hazard. Okay, Then I thought about let's do deep learning method. I didn't apply random forest, but neural network deep learning method maybe better actually. But uh, now is actually we made a deep learning method that's we did it, and now it's a lifetime data analysis is under revision. They asked 2 weeks ago. So Zhongjin is revising now. So here is deep learning. Many of you know this kind of neural network model. Okay, so deep learning enhanced BJ. Actually, I didn't make. We didn't make deep learning BJ method. Actually, already. Uh, Roman 2024 Statistics Medicine Journal. They developed a deep learning based BJ imputation. Okay, that's great. So we just replace boosting method to deep learning method in here. Okay, so that's the sensor observation on sensor case train DNN or log transformed outcome. Okay, so DNN predict log survivor. Loss function is a mean squared error. Okay, final prediction. So then same structure, we do iteratively, we find optimal treatment selection procedure. Okay, so we generate 1,000 patient, gender is just binary, tumor size, BMI, and then treatment assignment and in 0.5. Then we running the simulation study, then we apply right sensor in this case. Then this is we proposed the method actually. So these two stage cases with cumulation. So here's the output. BJ deep learning, see here, looks like Cox is not working properly. BJ deep learning is pretty successful in two-stage case. We did actually three-stage case, but referee said maybe two is enough actually. So we just reduced 3 to 2 actually. Then looks like no outliers here. Nice, working well. So successful. So then same data set we applied, then we found that kind of yeah, this box plot with comparison, okay, with Coxon test imputed Q values, then imputed Q values was the significant one with the test. Then looks like all three models actually, which this is our proposed models, that looks okay. They are significant, statistically significant. So in the distribution of imputed Q values between treatment, which is not evident from uncensored survivor data time. That means just to throw away the sensor data. Okay, so I think I just quickly review my three papers, and plus I just introduce Coppola method. That's the kind of also very working very well actually. Now it's under review. So I think more, I think this area is promising. I'm thinking to apply the computing event data. Computing risk in biostatistics. Some someone died because of not because of cancer, maybe some other factors, maybe car accident. You know, and it happens. So that's the computing risk we will consider. Okay, thank you for your attention.
Thank you so much for the talk. Any question from anyone?
Vinicius is doctor, so medical doctor. I'm not doctor. I hope I want to be doctor too, but I don't know much about medical data. I'm just statistician, so I just try to develop a nice method, and that's my job actually. So if you collaborate with a medical doctor, maybe it's more better method I can make in the future. Vinicius.
Yeah, John, I just wanted to congratulate you on your work, because we do have a lot of problems with missing data in healthcare, and many of the times we do have the data, but not in the format that we need in order to make good data analysis. So being able to input data, for example, for survival studies is I think it's a huge application. So for example, a team in a healthcare institution could work on making at least a fraction of the data right and use that to imputate the rest. I think that's a very interesting application of what you presented today. So congratulations.
Thank you. Also, this is good one is sequential decision, not only one time. Current method is just one time, okay? The sequential longitudinal data, medical studies, longitudinal data, main data, okay? So this is a sequential decision. That's the kind of main contribution, actually, okay? So, I think this censoring issue is to everywhere, actually, not only survival data. Maybe semiconductor, data too, actually. So this kind of idea can apply to many different, subject or field in AI as research area too. Okay, so I think data is very important. Okay, so issue is AI is you put the trash data, then you get the trash output actually. So that's the main concern, many people actually. So you put the trash data, you make a decision, then patient die, then who's responsible? Doctor or AI or Jongmin Kim? Who's the problem? That's the kind of insurance issue. So consider Vinicius make a medical insurance company for AI, treatment. Then you will make a lot of money to Vinicius. Okay. Anyway,
This
thank
year's
you, Ms. Dr. Orr. You thank you for a great opportunity to present. It's a nice community research trend.ai. I hope your team be successful in the future too.
Thank you so much for your words. I had one more question. If you have time. Oh, yeah,
I have time.
it's no, okay. So maybe one question. So you mentioned data. Since you mentioned data, I wonder if you're looking for realistic data.
Mhm. Yeah,
I see.
yeah. Real estate, actually, I'm not working at pharmaceutical company, so
Mm-hmm.
I try to get, but they're not allowed to use. Actually, they have this kind of data a lot, actually. But my place is a small place, so maybe it's good collaboration work with a pharmaceutical company. If they
Mm-hmm.
provide, then we can verify our method. I'm sure this method is working very well and promising. So I think, yeah, sometimes this collaboration, your pharmaceutical company will be promising and
Mm-hmm.
help people too. But that's confidential issue, so then doesn't want to open sometimes.
Yeah, they can get into trouble. Okay. Yeah, thanks for your answer. And thanks both of you for joining the session and giving a presentation. So as I told the other speakers as well, we continue the chat on Slack. So if you wish to be on Slack, then please be there, and the video will be put on YouTube as well. So there are many channels where speakers, I mean, the audiences can also reach you out and ask more questions. I'll try to kind of encourage people to do this. So yeah, it'd be great to keep in touch and let you answer more questions from the community.
Okay, thank you
So much.
Dankeschön.
Dankeschön. Thank you so much.
Bye bye.